Hello, this video now will be on Gauss's law, and we'll look at three cases where Gauss's law is useful, which are cases of symmetric charge distributions. And we look at the three cases that are cylindrical, spherical, and planar symmetry. So Gauss's law is just another form of Maxwell's equations, and this is the differential form of Gauss's law. Here we have it in terms of the electric field D. So these are the free volume charge density sources, and if we integrate it, we can also write it as, if we integrate this in volume on both sides, we get the volume integral of volume charge density, which is equal to the total charge enclosed in V. And we can also write this in terms of E. The divergence of the electric field E is equal to the charge, the volume integral, to the charge enclosed divided by epsilon 0, and here this is the total charge. If we are talking about E, and it has the permittivity constant, for D, because D is epsilon E, the divergence of D is just given by the free volume charge density. And if we apply the divergence theorem to this equation, that tells us that the volume integral of a divergence of a vector field is equal to the flux of that field through the closed surface that encloses volume V. So S and V are related in such way. So if we apply this theorem, now you can see that the flux of the field is equal to the total charge enclosed in V, or by S, by the closed surface S. And this is also referred to as the integral form of Gauss's law. So what's important to keep in mind is Gauss's law is, like Maxwell's equations, is always true, but it's only useful in terms of calculations when we have symmetric distributions of charges where it is easy to find the flux. So if it's easy to find the flux, then we can use this expression to get the magnitude of the electric fields. So we look at the first type of symmetry where Gauss's law is useful, which is cylindrical. And here we have a uniform line charge rho L, remember coulombs per meter. And the line is very long, so that around the line we expect the field to be only radial, outwards from the line if the charge is positive, and toward the line if the charge is negative. So this is the condition that comes from symmetry of our infinite long line of charge. And if the field has this form, then we can use a coaxial Gauss surface, so a cylinder with the same axis as our line of charge, because on this surface the flux on the side surface here, the flux is constant, because the electric field only depends on the distance r, the cylindrical distance r. So on a surface of constant r, the field is constant, and the flux will just be the magnitude of the field times the area of the cylinder. And remember, S is this closed surface, but on the top and bottom, the flux, because the normal to the surface is along plus and minus z, the flux is 0, because the electric field here is going to be parallel to this cylinder top, or here parallel to the bottom, and the S is parallel to Z, so the flux through these two top and bottom surfaces is 0, and the total flux is just equal to the side enclosed. Our surface X, the flux is just the magnitude of the field times the area of this side surface, and the total charge enclosed in that surface is the linear charge density times the height. We have coulombs, and I forgot here the epsilon naught, and from here we can get the magnitude of the field as rho L 2 pi epsilon 0 r, and this is given in volts per meter. And if we want to write the full electric field, magnitude and direction, we would bring back our unit vector cylindrical r and write it like this. So one checkpoint when you apply Gauss's law is to make sure that your result does not include any parameter related to the box. So our box here had a height h. I said any parameter, that's not correct, because the surface is a constant radius r that stays, and that's how we get the spatial dependence of the field. But it should not depend on any other variables that we choose for the Gaussian surface. So this is the field, electric field, due to an infinite line of charge. So in order for this to apply, this charge has to be constant. That's the only case when we can have a field that is just radial, right? Because from everywhere the field from left and right would cancel, and we only have a radial field, shown here as upward or downward. So the next case that we look at, Gauss's law, for spherical symmetric charge distributions. So here we will consider a sphere of constant or spherically symmetric volume charge density, rho v, given in coulombs per cubic meter. So we have a sphere of radius r with a uniform, so this should be uniform, a constant, or spherically symmetric. Charge distribution, so should not vary with theta or phi. Remember, phi is given from the positive x-axis, theta is defined from the positive z-axis. And if we have such charge distribution, spherically symmetric, we expect the field to be spherically symmetric and to only depend on the spherical, the magnitude only depends on the distance where we are. So the natural coordinate system to use is spherical, everything is symmetric, it only depends on, the magnitude only depends on r, and everywhere in space the field points only radially, no theta or phi components. So in this case, the Gaussian surface that we would like to use is a sphere of radius r centered on the origin. So this is our surface S, and to apply Gauss's law, the flux of the electric field through this closed surface S should be equal to the total charge enclosed. And if this field is of this form, then it's constant everywhere here on the surface of constant radius, and the flux is just that constant magnitude times the area of the surface. So we could express this in terms of the differential of unit vector and the differential area element at constant r, but in this case of constant field, we can right away see that it should be just the magnitude times the area. And now, depending on where our S, the radius of this green surface, is, if it's inside or outside of the blue volume charge density, the total charge will be different. So if we are inside, if R is less than it would be the volume R less than R0. R0 would be the blue, it's where we have charge. And once we are outside, for R greater than that, it would just be the total blue charge, R0 cube, and now we could write our final field. So we have these 4 pi's that cancel, and the field inside is rho v r epsilon 0 that I dropped here. We should have here, I always forget this epsilon naught. If we are inside the sphere, the field is increasing linearly with the distance. Once we reach the outside, the field just goes with the inverse square of the distance from the sphere. Okay. And because the charge, the total charge of the sphere is, this is equal to the charge of the sphere times 4 pi, our field outside can also be expressed in terms of the total charge of the sphere in the usual Coulomb's law form. And here we considered just uniform or spherically symmetric volume charge distribution, rho v, and because of that this flux became just the magnitude times the surface area. But if this charge density was a function of r, then we just have to take this actual integral to go from Gauss's law to finding the magnitude of the electric field. And the last and the third type of symmetry that Gauss's law can be useful with is planar symmetry. And the geometry here is a very large, like an infinite plane of surface charge area, surface charge density, given in coulombs per meter square. So if we want to find the field at some point away from the plane, you see that for each charge segment on one side there will be another. For these dq's, that will add at the points we are interested in calculating the field, so that the net field does not have any x or y components, but it's only a z field. So this is true for the infinite or very large plane of uniform surface charge density, so that the x and y components all add up to 0. And the only field is along z. So if this charge is positive, we have an electric field that points along plus z above and along minus z for a positive charge. And if the charge is negative, this z field would point towards the plane. So how can we find the magnitude of this field now? I'm going to draw just a line now representing the whole xy plane. And because this is the symmetry that we plus or minus above the plane, this is the symmetry we have from the uniform surface charge density. Our surface S that makes sense, where it is easy to apply Gauss's law, where it's easy to find the flux, would be this surface S. Like a pillow here, they call this a pillow box. Centered on the plane, so at the same distance. So where we expect from symmetry that the field has the same magnitude and opposite directions. Okay? So this would be our height divided by 2, and this is the field, our z field at this height. It has the same magnitude. So if you imagine this in 3 dimensions, in this case we can see that there's only flux, so this is our Gauss's surface S. There's only flux on the top and bottom surfaces of this box, because everywhere else the field is parallel to the surface. So it does not contribute to flux in or out. And this box has a certain area A and the height h. So our flux EdS through this closed surface S divided by epsilon 0. So this is Gauss's law. Is just going to be, because it is outward from the box, it's a positive flux for both top and bottom surfaces, and the flux is just 2 times that magnitude at h over 2 or minus h over 2 times the area of the box, and the charge enclosed is our surface charge density rho s times the area. And this brings us to this interesting result of the infinite plane of uniform charge, that the field magnitude is just given by the charge density of the plane, and it's constant regardless of how far we are from the plane, as we had seen for the infinite limit of the disk of charge. And from symmetry we had seen that the field should point away from the positive plane or towards the positive plane if the charge is positive or negative. So this is our third type of symmetry where Gauss's law is useful to find electric fields. So remember, it's always true but not always useful, and it is useful whenever we have cylindrical, spherical or planar type symmetries where it is easy to obtain this flux of the electric field.